Continuing with our discussion on Chapter 1, we're often interested in the types of samples that we can get. Why do we care where the data comes from in the first place? Well, the principle is actually very simple. GIGO, garbage in, garbage out. We cannot depend on getting a good statistical inference if what we put in as our data is terrible. If we don't have data that represents the actual population that we're trying to reflect in our statistics, we might as well hang it up, because any information that we get from that bad data is going to have bad results. So it helps to know that there are several different kinds of sampling that we can use. The most basic kind that most people know, although they never call it this, is called a sample of convenience. And it's a sample based on someone's expertise about a population. It's convenient, but not always close to reality. The quality depends on the researcher's expertise. So what are our kind of sampling methods? Well, there are a few. The most basic kind is called a simple random sample. In a simple random sample, every element of the population has an equal opportunity of being chosen. And in a random sample, a randomly chosen element can be considered representative of that entire population. And this is very good when we have a uniform population that does represent the group that we're trying to seek, but not always. Occasionally, it's helpful to have something called a systematic sample. If you think about objects coming off of an assembly line, it might be useful to choose every 25th item coming off that assembly line rather than every item coming off the assembly line in order to test. Sometimes that testing leads to our quality controls, and we call this type of sampling systematic sampling. On the other hand, sometimes our sample must be based on some other kind of feature, typically based on a geography of sorts. For example, when the population of a state like Rhode Island is sampled for political opinion, they could randomly sample the entire state, but more likely than not, the sample would just include residents of Providence, which is its largest city, rather than spreading out that sample to different parts of the state, such as Newport or Westerly or Cranston. So in order to be able to sample correctly, we cluster sample. We might choose a group of respondents from Cranston, East Greenwich, Westerly, Newport, and Providence, and ensure that we have an equal number of samples or proportional samples from each of those parts of the state. Another kind of sampling that's often done is called stratified sampling, and in stratified sampling, we're looking to find our sample based on a characteristic rather than a place. For example, men versus women, or people from different socioeconomic backgrounds, or people from different levels of jobs who are either union or non-union, for example. Those strata are based on characteristics rather than places. And we've already mentioned what a convenience sample is. True random sampling is often done with replacement, but for practical purpose, with replacement, that means that if a person or a thing chosen from a population is chosen, they are sampled, and it is possible through pure random sampling that that person is chosen again. However, for practical purposes, we use simple random sampling done without replacement. That is, if an item is chosen from a population, it cannot be chosen for a second go. In a sampling error, the process of sampling itself causes the errors, and factors are not related to sampling. And the thing we call a sampling bias is created when a sample is collected from a population where some members of the population are not as likely to be as chosen as others. We want to avoid sampling biases. Another measure that we use to talk about categorizing our data is called level of measurement. And the level of measurement is based on the level of mathematics that we can or might not be able to do with that data. The lowest and most basic level of data is nominal. Data that can be put into categories, we consider these to be names, or characteristics such as gender, hair color, eye color, and so on. Nominal data cannot be mathematically manipulated other than to say it could be counted. The next level of data up is ordinal data. Ordinal data is nominal data, but it can also be ordered in some logical manner. For example, if we think about movie ratings, or if we think about grades such as A, B, C, D, and F. Interval data takes it one step further. Interval data is typically numerical data. It's ordinal plus the interval is meaningful, but ratios are not. For example, if we think about temperatures on the Fahrenheit scale, one cold day in January could be 0 degrees Fahrenheit, and the next day could be 10 degrees Fahrenheit. But it doesn't mean it's 10 times as warm as it was when it was 0 degrees Fahrenheit. The only thing that matters to us is that there's a 10-degree differential or interval between those two numbers. The highest level of mathematical data is ratio data. Ratio data is interval plus data that has an absolute and meaningful 0 point along with meaningful ratios. If a race is run and a marathon winner runs in 1 hour, whereas another runner finishes in 2 hours, we'll say that the runner who ran 1 hour was twice as fast as the runner who ran in 2 hours. There's an absolute 0 to measure them against. They started at time 0 both, but one ran twice as fast as the other. When working with data in large sets, it's often very helpful to organize and summarize that data by constructing a table. No, not that kind of table. A basic frequency table has two columns. One column lists all the categories of the data, and the other column lists the frequency of each category, which is a number of data values in the category. For example, consider these list of 25 grades from a recent test. As we can see, it's a little disorganized, and we can kind of tell a little bit about the grades, but we get an even better story when we arrange the data in a table. And we see that there are 4 A's, 7 B's, 9 C's, 3 D's, and 2 F's. And this tells us a little something about the data. This is what we call a frequency data based on categorical or qualitative data. We can also do something called a relative frequency. The relative frequency of any category is the proportion or percentage of the data that fall into that category, and we find it by dividing the frequency in that category divided by the total frequency. So for example, for our grade of A, if we take 4 and divide it by 16, we can see that we get 4 out of 25, or 0.16. This data is given as a proportion, or 0.16 in decimal form. Please be very careful that on the assignments I ask you to give me this ratio rather than the percentage. If I ask you specifically for the percentage, then you might say 16%, which is the equivalent of 0.16, but that's the percentage. And I will inform you in the assignment when I want that number. But as a default, please use this ratio, or more specifically the decimal, as your answer. This type of data table is especially helpful when we have large masses of numbers. Consider this table showing gallons of fizzy cola syrup sold by 50 sales associates in a month. Although we can see the numbers in the table, they don't tell us very much, and it's hard to wrap our minds around that data unless we organize it somehow. One way of organizing it is to organize it into the numbers of gallons sold by categories. So we create categories in which there are data bins here from 80 to 89.9 and 90 to 99.9. We say that these categories of 10, we can count the number of employees who sold those amounts within each of these categories, and we can see the top sellers within each one. For example, most sellers sold somewhere between 110 and 119.9 gallons of their cola syrup. As before, we can create a relative frequency table, and we see that if we divide each of these numbers by 50, 7 divided by 50 gives us 0.14, which is the proportion that we want to know. But sometimes it's very helpful to know another number, and we call that the cumulative relative frequency. The cumulative relative frequency is found by adding up each of the categories below it. So for example, where we start with 0.4, the next relative frequency is 0.12. If you add 0.014 and 0.12, you get 0.16. This is to say that we now know that 0.16 of all of our employees sold less than 100 gallons of fizzy cola syrup. 36% sold less than 110 gallons, and 64% sold less than 120 gallons. Well, that's interesting because 64% tells us that the majority of our workers are selling somewhere less than 120, so our top group must be up here, this 120%. So we call that a cumulative relative frequency, and again, as we did in the relative frequency, you should be entering your answer in this decimal proportion type of format. Well, that's it for our discussion. Once again, please remember that you should be finishing your Chapter 1 assignment by Tuesday and Discussion Board 1 post by Tuesday as well. We'll begin covering Chapter 2 during Week 2, and I look forward to seeing you in class then. Good luck!